How do you begin a design? Starting only with a slight impression of an idea and somehow establish from that the foundation for a work of art. The white canvas of a 2D plane, or infinite void of 3D planes. Starting from here is a challenge, considering you're lacking the prime component which determines a design, materiality. In the same way that cooking ingredients determine the final taste of a recipe, physical materials determine the shape of what's to come for an artistic work. Adding sugar to a recipe dispatches the dish on a path towards sweetness. Salt and pepper towards a direction of something more savory. Concrete for a building, well, I wager you can imagine what forms will begin to emerge with this material in mind. Now, the white canvas isn't so blank. The design questions begin to compound as you MacGyver your way through the rest of the process. In design, you work with the materials that you have. In the decade of 20 BC, Caesar Augustus is presented with the first recorded treatise on architecture that we know of. The book written by the great Roman architect Vitruvius, not to be confused with Mount Vesuvius, though that too will make an appearance shortly. De Architectura, translated to On Architecture, but most commonly known as the 10 Books of Architecture, is a sort of Bible on buildings. Each of the 10 sections describes in detail Roman architecture and construction, everything from choosing the site of where to build cities for health, construction details on fortifications, and the ideal proportions of classical building. For now, we're interested in Book 2, where Vitruvius describes materials and specifically the Roman invention of concrete, meaning the material still used for freeways and skyscrapers goes back to the time of Christ and the Roman Empire. At that time, concrete was referred to as opus cementitium. The concrete dome of the Pantheon is one such example. For walls, Vitruvius describes opus incertum and opus reticulatum, methods of construction where cut stones are set along the outside of a 2-foot thick wall, where the inner core is filled with opus cementitium, aka concrete, albeit opus cementitium is a bit different to modern concrete mixes because the ancient recipe for concrete begins with a volcanic ash aggregate called pozzolana. In Vitruvius's words, there is also a king of powder, which from natural causes produces astonishing results. It is found in the neighborhood of Baia and in the country belonging to the towns round about Mount Vesuvius. This substance, when mixed with lime and rubble, not only lends strength to buildings of other kinds, but even when piers of it are constructed in the sea, they set hard underwater. In other words, the early volcanic ash used in Roman construction came from towns like Pompeii, which were later destroyed by Mount Vesuvius, the very volcano that provided the proper ash for ancient concrete. Pozzolana and lime, when introduced to water, start the chemical reaction to make cement material, necessary for Roman concrete. Vitruvius applied an interesting analysis on this process using Roman knowledge of chemistry at the time. See, with a belief in 4 key elements, water, wind, earth, and fire, this limited the scope of understanding chemistry at the time. He imagined that when pozzolana is baked in a kiln, the fire dries out the latent air and water within the earth, leaving pores in the substance. When water, sand, and gravel are added, the pores are filled in when the water eventually dries out. A stronger material is left. Similarly, the reason why concrete made with pozzolana volcanic ash dries effectively underwater is that it comes from Mount Vesuvius. Obviously, harnessing the fire inherent to volcanic ash balances out the element of water while concrete dries underwater. 2,000 years later, and we can do a bit better on explaining the mixture and reaction of concrete. The process begins with cement. Modern cement goes back to a mixture invented in the 1840s called Portland cement, which derives its name from a resemblance to white stone quarried from the Isle of Portland in England. But cement is not quite concrete. We have a bit further to go in the recipe before we reach that. The cement is only a binding agent that reacts with water to bind loose aggregates together, making concrete. In effect, man-made stone. Bridges, pavements, buildings, all structures cast in liquid stone. Concrete construction engineered precisely around human endeavors, such that any association to the natural world is divorced. But even the tallest skyscrapers owe their concrete frames to the same process that grows the skeletons of their creators.
Them bones, them dry bones, now they're the working of the Lord. Bones are heard of, but seldom seen, except each year round Halloween. But I've got a shockaroo. Right now there's a skeleton locked up inside of you. So please remember, you got to do it while you're young. Feed your bones some good old calcium. Drinking milk, a glass or two will help your bones to stay in shape and do their job for you. Your skeleton. It's a frame.
Similar to the growth of bones, calcium carbonate's reaction with water drives the solidification of cement. But milk isn't an ingredient in concrete. Rather, cement draws its calcium from lime, and not that lime. Lime is a general term that describes minerals rich in the element of calcium, typically calcium oxide or calcium carbonate, in either case most abundant in sedimentary limestone rocks. Subsequently, calcium-rich rock formations affected by water, like stalactites and also geysers, behave in a similar way to cement. Over time, the calcium-rich minerals react with water to solidify into stone. Dank caves full of beautiful stone formations, to animal skeletons, all the way to concrete frames. The process of turning water to stone is nothing new on planet Earth. Lime slated to become Portland cement is sourced from massive limestone quarries. At processing, the limestone is crushed, then dumped alongside shale and clay into massive spinning 900 degrees Celsius ovens. Inside, while rotating, the mix sinters, where immense pressure from heat compacts the rocks together into a single material, analogous to the Earth's deep underground churn, an unimaginable pressure cooker that compacts and bakes metamorphic rock. Our mechanized process isn't perhaps quite there yet, but we can at least bake these tiny little guys called clinkers. They're not long for this world though, as they are ground up into dry cement powder, shipped off in bags, slapped with a Portland cement label, then shipped all over the world for construction projects. This whole process is the most difficult and energy-intensive section of concrete construction. In a way, it's basically doing what the Earth does underground with the dense compression of rocks. Environmental sustainability complaints about concrete start here, as the cement kiln process generates large quantities of CO2. But we've been up to this process for a very long time, so engineers have made and continue to make massive improvements to the efficiency and sustainability of cement kilns. Plus, concrete is one of the best insulating building materials, so future energy used in heating or cooling a building is reduced. So, as with all exchanges, energy use with concrete has a trade-off. Realizing construction to completion requires significant work and energy which can't be cheated. Concrete's energy input is just front-loaded compared to other materials. Wood and steel, you've got multiple steps involved with processing, then assembling and joining the materials. With concrete, in very simple terms, once the cement is bagged, You add additional aggregate, pour water, it dries out, and you're done. Despite the esoteric views on concrete chemistry, the concrete mix Vitruvius and the Romans used yielded incredible results. Vitruvius's descriptions of water to cement ratios barely changed after 2 millennia compared to how we mix concrete now. Casting concrete is a process that is governed by the ratio of water to cement, a ratio of water weight to cement weight, a convenient metric because a bag of cement used for construction purposes almost always weighs 94 pounds. So in the field, mixtures are governed in weight with a bag as a sort of reference point. The way it works is that cement at least needs 25% or 0.25 of its weight in water to solidify, although 25% is quite low and hard to pour for concrete constructions, where most builders use water in a ratio to weight of 0.4 to 0.6. Past 0.7 and there is just too much water. A higher ratio of water reduces the strength of concrete, but more water also makes concrete easier to work with. We can think of baking. A wet cake batter is easy to mix and has no problem fitting cake molds, but a thick, chunky batter is a pain. You're standing there just scraping the hell out of the mixing bowl. So choosing the amount of water that should go into a cement mix is a balancing act determined by the project. And it's imperative to get the ratio right, because again, to reaffirm, the strength of concrete is determined by the amount of water. When concrete isn't strong enough to meet its design intent, there are severe, sometimes disastrous consequences to a mistake made in the mix. Unless you're a real foodie psychopath, this isn't as inconsequential as a cake being too moist or too dry. On sites, contractors check the consistency of a pour with a slump test. Simply filling up a cone and then turning it over like building a sandcastle reveals a slight slump to the mound, which is measured for the ideal height. No slump means low water amount, while a collapsed mound implies a significant amount of water, just like building a sandcastle. Yet, cement and water aren't even the majority of concrete's volume. That goes to aggregates. Close to 3/4 of concrete volume is made up of fine aggregates like sand and coarse aggregates like gravel. The liquid cement mixture holds together all these small rocks as a liquid stone. It works like this. Coarse gravel pebbles are held together by the cement mix. The compression of all the gravel bits pressed together gives concrete its strength to support large frame systems. Sand is added to fill in the gaps that still remain between the comparably larger gravel. Though care should be taken with big rocks found in gravel. Large stones and small concrete forms can compromise the strength of the whole mixture. The rule of thumb is no aggregate sizes should exceed 1/3 the depth of a slab or 1/5 the thickness of a wall. Sizes vary and often depend on where gravel is sourced. Riverbeds, recycled concrete, quarries, pretty much any set of solid stones can be used as aggregate, nothing soft like clay. These aggregates determine the surface quality of the final cast. Colors and texture too. Aesthetic choice also goes into aggregates. Gravel size and color have an effect on the look. For the intro cast, I set the top layer in rockite, a smooth, store-bought cement mix with very little aggregate. A quite fine and smooth mix that is reflected in the clean surface and its edges. The base I did in Quikrete, ready-made concrete mix that is rougher with larger gravel chunks, stronger than the rockite, but also designed for construction projects, so in a small model, the aggregate is too thick. Of course, my small project is a DIY model. On a real project, you can source aggregates directly from the building site. Taliesin West in Scottsdale, Arizona, one of Frank Lloyd Wright's personal homes and masterpieces, was built with concrete sourced locally, to a naturalistic and beautiful effect. Only miles away is Cosanti, also built with local concrete, but the surface quality here is quite different, which goes to show the subtle variations local earth has to a project. Compare either of these to the Boston City Hall, and despite the shared material, it seems like it's built from something almost entirely different. Finally, like adding some spices to flavor a dish, admixtures are dropped into the concrete pour as a means of influencing certain chemical interactions. There are numerous admixtures that engineers call for in all sorts of different jobs. For instance, It's common for skyscrapers to be built with expensive admixtures which smooth out the flow of concrete as the mix is pumped up hundreds of stories into the sky. Other admixtures affect how concrete sets in cold or warm climates. Then, we have the most popular admixture, fly ash. It's a fine powder that comes from the waste of burning coal or gas. Highly recommended for ecological sustainability, given that a portion of cement can be exchanged with it. We're basically swapping out a bit of cement that is energy intensive to create with fly ash, a waste product that's left over after burning coal. It's quite comparable to the pozzolana Romans retrieved from volcanoes. Thus, concrete made with fly ash is stronger than normal concrete, especially in underwater conditions, just like the Roman concrete of old. We've effectively done a modern take on the Roman mix with the use of fly ash, and in doing so, many modern constructions can now utilize the gained strength to swap stone gravel aggregates with lighter weight clay and slate aggregates, which you couldn't do otherwise. Now, with the concrete mix complete, there is the question of giving it shape. With concrete, the shape can frankly be anything. Of course, as long as the mixture has enough fluidity to fit its mold. The mold here is referred to as the formwork. An entire video could be done on formwork alone, but for now, it's relevant to point out the final surface quality of concrete depends in large part on the formwork. Often, this is plywood or stacked wood planks, either way, supported by diagonal braces. The brace is necessary to cover the outward thrust of the liquid concrete as it's poured in from the top and settles into the mold. And this wood construction is why concrete often has the surface texture of wood when seen closely, either a plywood or stacked plank surface accordingly. Don't like the wood texture? Try corrugated metal for a ribbed concrete, or metal panels for a clean, smooth surface. Then sandblast the whole wall to reveal the aggregates if you want something quite rough. No matter the choice, often what also remains when the formwork is removed is these little guys. The classic holes in the middle of concrete walls. These holes are remnants of form ties, another part of the formwork. In many instances, additional support is required to hold the walls together as the liquid concrete puts pressure on the sides of its molds as it dries. Engineers have solved this problem by tying bolts to either side of the formwork, which hold the wooden forms together as concrete is poured into the form and hardens around the ties. After the ties are removed, holes are left over that are then filled with mortar or more concrete. Above concrete walls and columns, there is the matter of elevating concrete slabs as they set. Formwork on floors is basic enough, effectively just a shallow tray with a form for beams and 1 and 2A systems when needed. Depth here equal to that of the slab, and extrusions for the beams. On high-rises with a floor slab and columns must be cast in stacks, we've got shoring techniques to hold up the slabs. Temporary vertical columns that support joists which hold an elevated floor slab as it dries. Shores can come in wood post formats or adjustable steel bars, not dissimilar to jacking up a car. Shoring is a common technique also used in all sorts of projects outside slab formworks, so they're quite common to see in all sorts of contexts. And keep an eye out for holes in concrete slabs, or, if not holes, cylindrical sleeves set into concrete forms. Because after hardening, structural concrete slabs can only be cut into at great expense, and even then, only with the approval of a structural engineer. So to ensure passage for plumbing or electrical lines, holes must be voided out of the formwork with sleeves early before concrete is poured. Other formwork options are modular systems like steel tubes, ideal for copying and pasting concrete shapes across a building, or, on the exact opposite side of the spectrum, unique custom-designed formworks for exotic shapes. With the amount of effort that goes into constructing these, the formwork could practically be a structure in of itself. Now, formwork removed, there is the final matter of drying out and curing the pour. With a slab poured, job seems done, right? Well, almost. There's a final step. When concrete dries, the moisture of the pour evaporates up, leaving the surface solid. However, There is a problem where the upper half of a slab is closer to the air and sheds moisture more rapidly than the mix below it. This leaves the upper half solid and the lower half still moist, so as the lowest section evaporates, the moisture moves up to the solid portion above and leaves a spiderwebbing of cracks on the slab surface, following the evaporative trail. Beyond looking god-awful, the cracks can compromise the structural stability of a slab. Of course, we see slabs every day without any of these cracks, and that is due to proper curing methods. For about a week after pouring, concrete needs to be kept moist so that the top of the slab stays consistent with the evaporation of the bottom. A number of methods can be employed here: spraying water, chemical mixtures, water leveling. Sometimes wet paper or plastic covers are laid out. Some projects call for all of these combined. Main thing is that the slab needs to stay wet and consistent for many days until it's fully cured. And even then, you can't eliminate cracks entirely. Due to the chemistry of chemical hardening, concrete shrinks as the water evaporates, and this will leave some cracks on the surface. Generally, these don't damage the structure of a slab, but they look quite unprofessional depending on the final design. So the solution, designers can choose where the cracks occur by laying out consistent seams. These are control joints, small lines 1/4 the depth of the slab, and either cut into a pore or voided out with a metal strip. So when shrinking happens during the curing, the control joints will interrupt the consistent geometry of the slab and concentrate cracks into themselves. The concrete still cracks, but the cracks are out of sight and out of mind. Control joints control cracking through either a consistently laid out grid or a custom design set into a larger aesthetic, which gives a functional reason to patterns cut into concrete slabs. So, like these at first seemingly aesthetic cuts, seams that radiate out as lines cast from columns or extruding geometry are control joints as well. Otherwise, slabs are prone to crack at interruptions in their geometry. And you can see too, by these cracks radiating out from the column and water meter, the sawn control joints follow a similar path as the cracks, albeit looking far more regular. After all this trouble with control joints to protect against shrinkage, long after concrete has cured and set, it can then expand with hot outdoor temperatures from the sun. Unfortunately, thermal expansion is another cause of cracks, an especially common fate for asphalt roads that are poured continuously and then when heated, expand out and crack. Sidewalks hide this by concentrating the cracking inside the control joints, but this doesn't work when concrete expands and then abuts against something it could cause damage to. Like sidewalk abutting up against a driveway, if a slab heats, expands, then crashes into its neighbor, there could be damage. More so if the case is a large civic project like road and bridge connections. In these instances where you have separate concrete systems at play, which expand independently of each other, control joints aren't enough just to hide cracks. Cracks must be avoided completely with separated expansion joints, open seams with space for concrete to move. At wall and slab connections or slab and slab connections, expansion joints are prevalent. Rubber strips and metal channels are a popular choice, as are open gaps filled with epoxy, and then, with bridges, metal interlocking teeth. Materials that will flex in and out without breaking as concrete expands in the day as temperatures increase, then shrink when the weather is cooler. Concrete used for bridges or structures that undergo heavy vibrating movement also requires expansion joints at connection points. Park Avenue, New York, runs above a large underground train line starting at the intersection of 97th Street and goes all the way to Union Station. At street level, large expansion joints run the length of the sidewalk and road. Easy to miss if you don't know to look for them, but impossible to ignore otherwise. When trains barrel through underneath the ground, the roads crossing above shank comfortably with no damage as the joints give plenty of room for the surface to vibrate without failure. Even buildings with minimal movements throughout the day require expansion joints to isolate floor slabs from walls and columns, because despite how hard designers try, buildings still shake and move, be it from the ground settling, shaking from human activities, or just wind. By isolating columns and walls from the floor slabs, both can move independently of each other without causing horrible damage. In constructions where there are separate structural systems, a slab won't butt up against a load-bearing column or wall, but have a small gap filled in with an expansion joint or left open. Recall the control joints from a bit ago. Combining those with expansion joints around columns is an even more advantageous system. At ground level on grade, columns touch the ground and are isolated completely with a large gap between the column and the slab. This is then filled in with its own smaller slab, leaving an expansion joint. From there, control joints radiate out to concentrate shrinkage cracking. So when you see groupings of detail and seams around ground connections, it's not just for aesthetics, but a symbiotic relation of grouping details and designing around real-world building problems. With all this design that goes into joints, you'd think that we're at the end of it, but there's one left. Fortunately, it's much simpler. The construction joint is added purely for aesthetic reasons or for ease of construction. Nothing too special here. This joint marks where the formwork for one pour ends and another begins, basically open gaps that indicate separate concrete forms. While construction joints can work as expansion joints to stave off thermal cracking, these joints aren't placed exclusively at connections to walls and columns and such. It's effectively a mark that reveals the process of construction and distinguishes individual slabs. If a slab is damaged and needs to be replaced, it's swapped out at the construction joint. Over time, as the earth settles, separate slabs can then move with the ground and vary with the terrain. Now, as an added benefit, construction joints are opportunities, borders to transition between different colors of concrete or surface definitions. And speaking of color, pigments can be added to a concrete mix as an admixture. Numerous colors are available and quite cheap to use. Much better than paint, as stained concrete won't have its color fade or be chipped away at. If a specific surface texture is desired for a design, stamping mats are placed on the concrete during the cure, basically a tileable pattern stamped on the surface of a slab. This way, you could have cobblestones on concrete, a nice tile pattern, or perhaps a wood-looking finish. If instead smoothness is desired, contractors can use a polishing machine for a clean, polished slab. The Imagineers of the Disney parks do finish and joint techniques better than anyone, with intricate patterns and colors set into the concrete pavements at the parks. Look at the beautiful surfacing of the ground at Tokyo Disney Sea's mysterious island. Seams, stamps, and colors interact with the surrounding architecture before blending into Victorian-era stonework, a mix of industrial sci-fi and Victorian artistic flourishes, fitting for the story of Captain Nemo's Vulcania layer. We started at early Roman concrete and ended up with how concrete is cast millennia later. That's a lot of material, and we haven't even reached reinforced concrete yet. Stay tuned as we continue our journey into the next phase of concrete construction. So, the concrete mix is in place. It is poured, set in the formwork, and cured. The process then takes 2 to 3 weeks for concrete to reach enough stability for structural load bearing, 99% strength. But it won't ever make it over that last 1% to hit 100, as concrete never stops hardening. It gets stronger over time, though to diminishing returns. Look at the Roman Pantheon, constructed around 110 AD. The building, almost 2,000 years later, still features the world's largest unreinforced concrete dome, and still, this ancient concrete continues to get stronger. But in the present, we now have methods for achieving similarly impressive results. Through the process of casting liquid into stone, mimicking the natural rhythms of geology, we've remade the Earth's surface in a concrete grid to match our ideal living conditions. Men before us, and those living among us, cast their own mountains to hold back rivers. Through engineering, structures have been made immune to erosion and to earthquakes. Architects have designed concrete masterpieces that rival the beauty of nature. Granted, we're cheating. If you're coming from my video on concrete frames, you're familiar with the trick we're playing here. Our man-made stone can only rival mountains in nature because we've hacked the material and put inside steel. Concrete, like stone, is a brittle material, incredible in compressive strength, but under too much pinpoint pressure, it breaks. Picture a pickaxe chipping at rock. Beams succumb to this via the heavy pulling force of tension. As a beam is loaded with compressive force, tension concentrated at an unsupported point would tear past the material's surface and fracture internal structure. For more info on tension and compression, see my concrete frames video. If you haven't seen it yet, pause this and watch it. For those of you caught up, let's continue. The strength of materials is measured on a stress and strain graph. Stress on the vertical axis measures the amount of tensile force being put on a material. The horizontal axis points towards the amount of strain a material undergoes before breaking. Measuring tension, concrete has a rather gradual curve to climb before fracture, but still, an elastic material puts tension through the wringer. Resistance is a steep climb before yielding, at which point steel begins to deform. See, steel has a unique elastic property where up to the point of yielding, it will bend back to its original position when pressure lets up. After yielding, steel is permanently bent and deformed, but not broken. Steel can withstand greater tensile stress after being bent, but it will eventually fracture, albeit far after concrete. Architecturally, we're able to take advantage of the period where steel deforms before rupturing. Deformation of steel is a warning and gives time to evacuate a structure before it fails and potentially harms someone, while concrete fractures under lesser tensile loads suddenly and without warning. Despite concrete's failure to still in this area, its considerable compressive strength, among other positive qualities like fire resistance, are advantageous for construction. So, in the 19th century, engineers applied these advantages with those of steel through the invention of steel-reinforced concrete. Reinforced bars, or rebar, are embedded within structural concrete members. While you could just put entire I-beams in concrete, and that does happen, rebar is less expensive than full steel beams and also easier to work with. Steel rebar is distinguished with spiral or ribbed bodies for added grip within concrete. The cylindrical bar sizes vary based on nominal numbers 1 through 10, each number corresponding to a different rebar diameter. Number 5, for instance, is 0.625 inches in diameter. Structural engineers then use advanced equations to determine the size of rebar needed for a job. Take the equation factored moment equals 4 times the area of steel times the effective depth, which solves the tensile strength of a reinforced concrete beam. Don't worry about the complexity of the equation. It's basically stating that the maximum strength before failure is the area of steel multiplied by the depth of the concrete beam. In other words, both the depth of a beam and amount of steel in it contribute to a member's ability to resist force. Recall that in the previous concrete frame video, that increasing a beam's depth increases its resistance to tension, as more material is added to resist bending. Increasing the amount of rebar inside a concrete beam also makes sense because if steel is better at resolving tension than concrete, we want more of it, which leaves us with the way rebar is inserted into concrete. To be economical with resources, we want to use only what is required. An entire concrete beam made up of a spider nest of rebar isn't always required. So, generally for beams, rebar is concentrated at the bottom of a beam where tension is strongest. Perhaps even 3 rods are inserted rather than 2. Perhaps 4 might be required for a heavier job. 2 could be inserted at the top in instances where tension is on occasion reversed, like in an earthquake or hurricane, events where gravity causing tension is nullified and overtaken in power by even more wild outside forces. Allow me to become such a force and demonstrate. For the sake of testing the tensile strength of reinforced versus non-reinforced beams, we will use not concrete, but plaster of Paris, still a cementous material, but far less strong than concrete. Household items will break plaster. Test subject number 1 is a completely unreinforced plaster beam. Test subject 2 is similar but has thick wires inserted to act like rebar. The unreinforced beam breaks instantly upon dropping a heavy load on him. No sign of stress before destruction. His brother, test subject 2, a prime specimen of reinforced strength, takes a couple collisions before he breaks, and even then, the rebar holds, which mimics the failure of a reinforced concrete beam. The concrete will crack before the rebar fails, and is thus a visual indicator that you should get as far away from the structure as possible. Concrete columns too undergo tension where heavy weights above can cause buckling at the side, or sideways lateral movements like earthquakes make a column behave like a beam, by applying lateral force at the sides. As such, columns also are imbued with rebar skeletons. Buckling especially can happen on all sides, so columns are reinforced symmetrical across, unlike beams. Longitudinal bars within beams and columns have in the past busted out at the sides under heavily buckling or through wear and tear over time. An innovation made to fix this problem was to introduce transverse supports, or stirrups, rebar ties that are arrayed transversely across a member to tie the longitudinal bars together. Just like its namesake with horse riding stirrups, these guys hold the main longitudinal bars together, smaller in diameter to the main bars, as they're a secondary element, and in implementation, they're laid out horizontally to build a steel cage within a concrete beam or column. In cylindrical columns, stirrups in a linear array can also be spirally oriented for additional strength, with the primary reinforcements vertically arranged in a radial symmetry. Comparing stirrups of the past to modern-day implementations, it's apparent we build much denser cages. After earthquakes like the California Northridge quake in the 90s, engineers found poor performance from columns where larger gaps sat between stirrups, characterized by flattened columns with innards spilling out at the sides as if the columns fought in the Battle of Normandy. Today, to compensate in seismically active zones, rebar can be so dense the whole construction seems opaque. Beyond rebar, colossal concrete freeway bridges and other large structures are reinforced with a method called post-tensioning, a reinforcement option that replaces rebar with tension cables embedded within concrete. This in itself is a massive subject and deserves a video in its own right. But to quickly give a brief introduction, post-tensioning allows considerably greater spans between columns than that of typical rebar. Tension cables are especially designed to resist tension, hence the namesake. So it's a natural progression to replace steel bars with these guys. Unfortunately, outside a long span of a slab or a beam, it's hard to tell if these are even used, as they are inside the concrete and thus not exposed to see. On the surface, seems like normal reinforced concrete, save for destroyed structures where the pouring of cables is palpable. A more outwardly visual representation of the system is artistically portrayed with the Portuguese National Pavilion in Lisbon, Portugal. The space frames an impressive view beneath a sweeping concrete one-way slab. It basically looks like a tarp or some sort of fabric, but it's solid concrete. A magic trick in materials achieved through the embed post-tensioned cables hung between two concrete structures. The internal cables aren't all the way taut and thus have a swoop in how they're hung. Aesthetic design reflects the structural conditions within. And to some level, each structural and construction system throughout this video does the same thing, albeit on a smaller scale. Formwork gives a direction to the surface quality of concrete surfaces. Joint design dictates visual seams. The entire concrete mix process itself is insight into the achievement of doing what the earth does with stone. Materials give a range spanning from the influence of a design's details, or, like the Portuguese pavilion, the whole concept of the work. So remember, the next time you're staring down a canvas, deciding that concrete will be the material expressed, there will be a certain pull and inevitability of form and detail imparted on design.